Hello everyone, this is Dr. Lennon. So today we're going over a couple of sections on triangles and polygons, just some basic things, and then the next section we'll look at some basic facts about circles. So let's start with triangles. So everyone knows a triangle is just a three-sided figure. So there's some two main things, I guess we could say. Well, maybe we'll say three. So let's say three facts about triangles. These are the most basic facts before you get into trigonometry and stuff like that that we kind of encounter the most. So I believe we already talked about one in the angle measurement section, so we won't repeat that, but you know, the sum of the interior angles totals 180 degrees. Another one, though, that we're focusing on in this section is the area formula. The area is 1/2 times base times height. And the third one is the famous Pythagorean theorem, although this only applies to right triangles, meaning triangles that have a 90-degree angle. So, given a right triangle with hypotenuse, we'll say lowercase c, and legs A and B. So basically that looks something like this. So the hypotenuse is just the side of the triangle that's opposite the 90-degree angle, making it the longest side, and the legs are the two shorter sides. Then we always have the equation a squared plus b squared is equal to c squared. So let's look at some of those facts. Let's start with just some examples. Maybe, computing an area. So we'll start with find the area. So we'll say A, maybe we have some triangle that, it's not so regular, but maybe we happen to know that this base is 10. And we don't know the either two sides, but maybe we know that this height right here happens to be 6. Well, then the area here is just 1/2 the base, which is 10, times the height, which is 6. So that comes up to 30. So notice that knowing either of the other two sides doesn't really help us here for finding the area. You do need to know the height. There is a formula known as Heron's formula that will allow you to find the area knowing just the three sides, but we're not going to go over that in this course. Okay, B. Maybe we have an equilateral triangle. So this equilateral triangle is kind of a special case. So that means all the sides have the same length. So let's say we have 16, 16, and 16. Now for this example, since it's equilateral, that means if we drop a perpendicular line to the base here, that will actually bisect the thing below. So we know the base, and we know this. So if it bisects the base, that means that this would have a length of 8. And then to figure out the height, we could actually use the Pythagorean theorem. So if that's h, your two legs are 8 and h, and your hypotenuse of the right triangle that we formed is 16. So we know that 8 squared plus h squared is equal to 16 squared. So we have 64 plus h squared has to equal 256. And then we want to subtract 64. So we will get that h squared is equal to 192. So h is the square root of 192. And we can give a decimal approximation for that since we're typically dealing with measurements in this class. So that comes out to about 13.86. So now that we happen to know the base and the height of this triangle, we can determine its area. So the base was 16. The height we just figured out is 13.86. So our area for the above triangle is going to be 1/2 times 16 times 13.86. And let's see what that comes out to. So that is 110.88. And then for C, let's look at one more where maybe we have things kind of given to us in a different order. So let's say, given the triangle, the figure below, sorry, this is, oh, I've already got it. So given the triangle, let's say that looks like this. Suppose the area is 64 inches squared. What is the value of y? So basically we just plug everything we know into the area formula. So we know the area is 64, we know the base is 16, and we know y is the height. So this is a 90-degree angle, so y in fact is the height, if that was not clear. So 64 is equal to 8 times y. Divide by 8, and we get that y is equal to 8 inches. Remember, the side lengths are all inches, even though the area has a different unit, inches squared. So that's it basically for the basic problems here. Let's look at a couple Pythagorean theorem examples. So example, we'll say find the missing side using the Pythagorean theorem, and these are pretty straightforward. So if we're using the Pythagorean theorem, that's a squared plus b squared equals c squared, and that means all of the triangles we're dealing with are right triangles. So let's suppose, I don't know, we have a triangle that looks like this. Again, these are not necessarily drawn to scale, but you get the idea. The box indicates which angle is the right angle. So let's say this has length 20. So excuse me, let's go ahead and make the longer one at least look like the 24. So let's say this is 24, this is 25, and this has side y. So the legs are 24 and y. So we know 24 squared plus y squared is equal to 25 squared. So go ahead and plug them into your calculator. So we get 576 plus y squared equals 625. And then we want to subtract 576 from both sides. So doing that leaves 49 on the right hand side, so y squared is equal to 49. Normally we'd have to have plus and minus the square root, but again this is just a distance, so that means it is a positive value only, so we see that the value of y is 7 for this problem. So let's go ahead. So when you have one of the sides of the hypotenuse, things are going to involve some subtraction. If you have both of the legs, usually it's a little bit easier. So the most common right triangle that you encounter, or at least the ones with the smallest integral values, is this one right here. So let's say we have 3, 4, and let's call this side z. So the legs are 3 and 4. So in this example, 3 squared plus 4 squared must equal z squared. So we have 9 plus 16 is equal to z squared. So we have 25 equals z squared. Take the square root. So the square root of 25 is the value of z, which happens to be 5. So your answer for part B here is 5. So if you have three integral numbers that when you add the squares of the legs and you get the hypotenuse, these are what are known as Pythagorean triplets. So there's actually a whole family of these type of numbers that come up in practice, but for us, a lot of them times we're going to involve decimals, so they don't have to come out so nicely. So I gave 2 examples where they did come out nicely. Maybe we'll do one more where the answers don't come out so nicely. So let's just make up some random numbers and see what happens. Again, they have to make sense because the sum of the 2 legs has to be greater than the hypotenuse. So let's say we have something like this. Let's say we have a right triangle where the hypotenuse is 15 and the other leg is let's say this is equal to, so let's go ahead and let's go ahead and say let's say the height of this right triangle is 10. So we want to find the missing side, x. So again, the same sort of process. So let's just do this over here. We know that x squared plus 10 squared is equal to 15 squared. So we have x squared plus 100 equals 225. So we just want to subtract 100 and take the square root. So x squared here is 125. Which means x is the square root of 125. So I'm just trying to make my x's a little more clear. That's not going to come out nice. It's not a perfect square, but we can always approximate it with a decimal if we have to use it for a measurement. So to 2 decimal places accuracy, this is about 11.18. Okay, so that's pretty much it for the triangles component here. We do want to talk a little bit about, I'll mention one thing about regular polygons and one other thing they kind of have on the homework that more of these things we can investigate when we know some trigonometry, but for now we'll just present it as kind of like a random fact. But so a definition, a regular polygon is one that has all sides having the same length and all angles having the same measure. So, I mean, just for example, we know a few of these. The equilateral triangle, what's going to happen? Well, all sides would have the same measure x, and then all of the angles would be 60 degrees. All 3 angles would be 60. The regular quadrilateral, the regular 4-sided figure, is the square, and all sides, again, would have the same length. You could call them x, and so on. And this is not super duper interesting, but there is one interesting fact that comes up on the homework. So consider the regular hexagon. So this figure right here, so regular 6 sides with all sides having the same angle measurement. What happens is if you look at this long diagonal that goes from any of the 2 things, this diagonal right here across, let's call it D. If we have one of the sides, one of the regular sides, X, it turns out that the diagonal here, D, is exactly equal to 2 times X. So that's true for the hexagon. It's not true on, say, like the square. For the square, it would be something like the square root of 2. So that comes up in one example on the homework. I think they, so for instance, given the regular hexagon, so let's say we have it right here. Oh, I don't know. Let's say this side length is x. If I, sorry, not x. I need to give you some numbers since we're doing an example. So let's say, I don't know, let's say it has side length 7 meters. Find the length of the diagonal D here. So let's say find D. So we know that D is just going to be equal to 2 times 7. So the diagonal of this hexagon would be 14 meters. So that's just one kind of fact that comes up. I'll mention one more thing. So one kind of thing that comes up a lot, proposition. And we won't really do anything with this, but it is good to know. The sum of the interior angles of an n-sided polygon is n minus 2 times 180. So we knew already that a triangle had an interior sum of 180 degrees. Well, this gives it to us for any polygon. So let's just write down a few so we can kind of get the idea. So we saw that triangle had an interior sum of 180. If we look at 4, that's a square or rectangle, that has an interior sum of 360, which makes sense because the square has 4 90-degree angles. And notice that's 4 minus 2, which is 2 times 180, 360. 5, we get 540, and so on. So this pattern continues is essentially all that that's saying. Okay, so that is the basically it for 8.3. Let's just talk about 8.4 briefly. So we just talk about the circle. So let's see, I thought I had a new section here. Oh, I kind of flip-flopped these. So I will have to switch them around. Let's make this a new section. So back in here, so we'll call this 8.4 circles. So this is the circle section. So basically, for right now, we're not talking about any analytical geometry. We're just talking plane geometry. So how would you define that? Well, a circle is the set of all points a fixed distance from a central point. So again, those are your two components. Have a circle like this, that dots your center, and the fixed distance there away is the radius. So r is the fixed distance, known as the radius. If you double the radius, d, which is twice r, which is what you would get if you went all the way across through the center. So this would be d. This is known as the diameter. And there are two formulas that come up from the that allow us to figure out both the area and the circumference of the circle. So two formulas. So the first is the circumference, which is essentially the perimeter, the distance around the circle. So this is given by the formula 2 times pi times r, where pi is the mathematical constant that can be approximated by 3.14. In fairness, it goes on forever and ever and never has any discernible repeating pattern. So a lot of calculators now have a button that you can use pi, so it gives quite a bit more accuracy than just using 3.14. And the second one is the area, so the area of the circle is given by the formula pi r squared. So let's go ahead and just do a couple of examples, and then we will call it a day. So find the circumference and area of each circle. So A, let's suppose we have a circle, and I just give you the radius. I don't know, let's say it's 12. Let's say 12 meters. So for this one, again, the circumference is 2 times 12 times pi, which is 24 pi, or we can approximate that. That comes out, if you round to 2 decimal places, that will be 75.40. And just like perimeter, this just has the units meters. It is just whatever the same distance measurement is for the radius. Whereas area is going to be square units. So when we do the area of this circle, we're going to get pi times that radius, 12 squared. So this will come out to 144 times pi, and you can do an approximation of that. And the approximation here will be 452.39 if you round to 2 decimal places. And again, since this is an area, it's going to be meters squared. All right, let's look at B. So let me give you another circle, but maybe this time I give you the diameter instead of the radius. So let's say we have the diameter of the circle, which is given by 15. So now, if D is equal to 15, that means R is equal to 7.5. Why don't I give, let's say this is inches. I don't know, so the diameter is 15 inches, the radius is 15 inches. So our circumference here is going to be 2 times the radius times pi, which is 15 pi, which again, if we approximate that, is 47.12 inches. And the area would be 2 times, excuse me, not 2, it's pi r squared for the area. It's just kind of doing the same thing over again due to repetitiveness. So we have pi times 7.5 squared. So that would be 56.25 pi, which comes out to 176.71. And again, that's going to be inches squared because this is an area. So I think for the time being for circles, that's as complicated as it's going to get, just looking at some circumferences and some areas. Again, if you take some analytic geometry, you can look at some algebraic coordinates to give equations of circles. We're going to be looking at applications with circles, but only after we do a little bit of right triangle trigonometry. But for this section, that's going to be it. So I hope everyone's doing well, staying healthy. This is Dr. Lennon signing off.